Thank you, Victoria. It's very wonderful to see all of you here. Thank you very much for being here. And I know that it's fairly late in Vietnam. And so we will make the session as simple as possible to follow. And I will try and cover most of the important features of PIPENET. And as you know, PIPENET has 3 modules: the standard module for general purpose applications, the spray sprinkler module for fire protection systems calculations, and the transient module for dynamic calculations. We will look at all 3 modules by taking actual examples. Today, I will not talk much about input because the input of PIPENET is very, very simple. But we will try and concentrate on applications of PIPENET because we're all engineers and the applications are more interesting for us. So that is what I plan to do today, to look at some applications for each of the 3 modules. Before I go to the applications, I will just describe the desktop of PIPENET. This here is called the drawing area, and you can see the drawing there, and there is some colors, and the colors can be indicated by these 2 panels. And if I want to look at the attributes of an item, let's say that item there, I click on that, and the data is shown here for that item which I've selected. And also, if I've already done a calculation, it shows the results. So that is this window here is called the properties window, and that is the drawing area. Now I can zoom in. And if I see this on the desktop, on the drawing area, I don't know where I am. It'll be difficult for me to find out. I can show the labels. I can show the item labels and try and remember, but here you don't have to do that with PIPENET. You have a schematic overview. It shows the complete network, and within that it puts a box which indicates what is in the drawing area. And the selected item is red here, so that corresponds to the item which is red. Also, you can see that on the schematic it's red as well. If you go to the data window, see that item is also selected in the data window. So all 4 windows work together. We've already seen the drawing area, the properties window, and the schematic overview. This window is called the data window. It is a bit like a spreadsheet. It has comprehensive information about several item types. This is pipes. I can look at the results. See, it shows the maximum pressure, maximum velocity in the pipes. If I want to look at, let's say, pumps, There are 2 pumps in the system, and they're shown here. And if I want to go to a pump, I click on that, it'll take me straight to that pump. I can have a look at the results for that pump. So it is very, very fast and very simple and intuitive. That is one of the beautiful aspects of PIPENET. Let's have a look at pipes. Now, because this is the transient module, it is dynamic and the velocity can change. So each pipe has a maximum velocity. So for example, pipe 1 has a maximum velocity of 5.88 meters per second. Now, one thing that will be of interest to me is to see where is the pipe with the maximum velocity amongst all the pipes. So I can click on this. This is a very important feature. It's called sorting. Click on maximum velocity. It reorders the pipes in increasing order of maximum velocity. Click again. It's decreasing order of velocity. I want to know where is this pipe, the velocity of 5.88. I click on that and it shows me immediately where is that pipe. And you can see that on the schematic overview. It's that pipe has the maximum velocity. It's very, very easy and very useful. And that is what makes the PIPENET such a powerful tool, because it has all these tools which enable you to work quickly and optimize the system. By the way, using PIPENET is not only about doing calculations, it is about optimizing the system, and each network that you design using PIPENET, you will save many times the cost of PIPENET because of optimization you can do. You can, for example, reduce the pump size, reduce the pipe sizes, and so on. This enables you to save a lot of cost in capital cost and operating costs. And they are many, many times more beneficial to the customer than the cost of PIPENET. That is why, one reason why people use PIPENET such a lot, because it's a very quick way you can save costs. Anyway, this is a layout of PIPENET. The first module of PIPENET I'd like to show is the standard module. It's the simplest module. It's a very powerful program. I'll open that. It's a closed loop cooling system. See, I can even maximize that screen and then right click, scale to fit. See, we're asking for the pipe size, and the pipe size is unset. If you go to the data window, you can see that the diameters are not set. And if you click on a pipe here, you can see that the diameter is not given, but the length and the elevation change are given here. And also the pipe schedule is shown here. Now you may be thinking, well, you know, I work with fiberglass pipes. How can I input the pipe schedule for fiberglass pipes? I can go to library, schedule. I can create a new pipe schedule if I wanted to. I will not do that right now. But if you click on new, you can actually create a new pipe schedule. There are many, many other things you can create. You can create pump curves. You can generate your own fittings data and so on. So that's in the library. For example, if I wanted to create a long radius bend, new, see, I can create a fitting called BE01. R over D ratio of 3.5. There are different types of fitting. That is it. See, now it'll be in this list of fittings. And if I want to add that fitting to that pipe, I select that pipe, fittings. See, this ROVD ratio of 3 is there. I can add that fitting to that pipe. Or if I didn't want to, I can also remove that fitting. Anyway, the first step here is to calculate the pipe sizes. So you can see that the pipe diameter has a yellow background, which means that PIPENET will calculate the diameters. So keep your eye on this. See, it's determined the pipe diameters. You can also see that on the schematic. How does PIPENET determine the pipe size? See, I've selected the pipe schedule. I've given a maximum velocity. Based on that, PIPENET calculates the pipe diameter. In the tabular output, we go right to the end. It'll give for each pipe size the length of pipe. So you can do cost estimation using this. And I want to try now to optimize the system. So what I'm going to do is to increase the maximum velocity to 6 meters per second. These are the old values, and if you keep your eye on this, you can see that this will change. See? Because I'm allowing a higher velocity, the pipe diameters are smaller. The diameters are shown here. I can look at the velocities. If you remember, the maximum velocity we allowed was 6, and here they're all below 6 meters per second. So let's look at the diameters. See, this diameter, 125 millimeter, is not a preferred size. In normal engineering, we do not use this size. But because I allowed PIPENET to select the size, it has chosen that size. So what am I going to do? Go to pipe type. It's 125. Avoid in design, and it puts a red mark indicating it's not allowed. And as you can see, the diameters have gone. Now, it's done the calculation and selected pipes which are allowable pipes. What I want to do now is to maybe select the pump. So what I can do, see, I've shown the pressures and the flow rate. So you can see that the pump needs to generate about 17 psi. You can see the units here and also here. And you're thinking, what is this US gallons per minute and PSIG? I want to see in metric units what you can do. Go to units, and you can go to metric units. What also you can change the pressures individually. See, now you have the results in bar and cubic meter per hour. So I recently come across companies from Vietnam who are working on overseas projects. And in such a case, your customer may prefer units that you're not familiar with, in which case you can use the units you're familiar with and do the design and optimization, and in the end change the units, and you will have all the results in your customer preferred units. So that is another beautiful feature in PIPENET, that you can work in the units you're familiar with. That is very important for you. Okay. So what I'm going to do now, see, we've calculated the pipe diameters. I must now fix the pipe diameters, because if you remember, the pipe diameters changed when I changed the maximum velocity. In the same way, if I change some flow rate or something like that, the diameters will change. I don't want that because I have finalized the design. I want to fix the diameters to these values. To do that, I will go from B to A. See, it will now fix the pipe diameters. I'll click on OK. If I need to refresh this. You can see that the yellow background is not here anymore. That means that PIPENET cannot change the diameters, but I can change the diameters if I wanted to. So the user can change the diameters, but PIPENET cannot automatically change the pipe diameters anymore. So let's have a look at flow rate and the pressure. Let's go back to the units that we had before. The pressure was in PSIG. The flow rate was in GPM. If you have to show the results in GPM, do remember that the gallons per minute in the UK is different from gallons per minute in the US. So I would make a note of this. The pump requires a flow rate of 900 GPM, and the pressure difference is 16.983. So you see now we've determined all the pipe diameters. Also, we know the capacity of the pump, which is required. So what I have to do next is to insert the pipe. Also, if there is a system that's completely closed loop, you cannot do the calculations because the pressure can be freely moving up and down. And in a system like this, there's a makeup tank here, and the makeup tank will actually set the pressure in the system. So then that is the next stage. I'll open this file. See, I've done all this. This is the system with the pump. I will open that. I input the pump curve in the library. See, these are points. What we needed was 900 GPM, and the minimum pressure the pump had to generate was 17 PSI. And I've chosen a pump that's slightly bigger than that, and I've taken points from that and input them here. You can see that now I've input the pump. Here I've broken these two that node connection to the makeup tank into two nodes, and I've set the specification to be 60 psi on both nodes. In reality, this is one point at which the makeup tank is connected, and that is what I'm doing here. So this is a complete system. We went through many steps. First of all, we did the pipe sizing. The pipe sizing, we did calculations with different design velocities, and then we optimized the system in that way, taking into account the capital cost and the operating cost, the power consumption of the pump. And then we select, and then we try different velocities which produce different sizes, and then we fixed the diameters when we were happy with the design, and then we inserted the pump and did the closed loop calculation. So it is a complete design process. And of course, if your system is already designed in the sense of you already know the pipe diameters, you can input them yourself manually. So that's this example. What I will do next is a closed loop system. What I will do next, still with the standard module, I'll take by the way, PIPENET is not only about cooling water systems. I'm taking cooling water systems because every plant has cooling water systems, and so it is a very common application. Scale to fit. You can maximize scale to fit. Then you can show pipe. Now, what are you thinking? Yeah, looks nice. Let me just make the font size a little bit bigger so you can read it. And you're thinking to yourself, yeah, it'd be nice to have this as a schematic drawing. PIPENET allows you to do that. File, print preview, page fit. You can also set up the page, but I won't do that here. You see? Now, you can see that it is showing the network with all the data, all the colors, and the color coding is shown here. And then you can copy and paste this into your Word document or print it and include this in your Word document. Anyway, it's here. In this case, all the pipe diameters are fixed. So what is unique about the system? This is a steady state calculation. The diameters are fixed, but there are controllers in the system. If I click on that valve, it becomes red, indicating that that's a selected item, and the attributes are shown here. You see, this is a control valve. What does it control? The flow rate, the set point, and the pipe on which you're controlling the flow. So where is pipe 42? You can go and search for pipe 42 here. Oh, that's pipe 42. Or alternatively, you can actually show the pipe labels. So valve number 3 controls the flow rate in pipe 42 to 3,000 cubic meters per hour. It's a fairly big system in terms of, for example, this pipe is 1.5 meters in diameter. It's not a huge system, but it's quite big. What about the pump? See the pump? It's called RLC pump. See, that is in the library. As we saw earlier, these are points from the library. So you can see that the pump curve can have different units. See, so because the pump curve given by the manufacturer may not be in the same units as the units in which you're working. So you can change the units for the pump curve here. But anyway, this is the pump curve for the pump we're using in the network. So let's see what data we're giving. See, the pump is on. There's no sensor, but we're setting the speed of the pump. So we're setting the speed of the pump manually without an automatic control. And the pump setting or speed is always between 0 and 1. 0 means the pump has stopped. 1 means the pump is running at its design speed. So this is running slower than the design speed. That's the pump's performance curve at the design speed, and that's a performance curve predicted by PIPENET at that speed. So the pump is also variable speed pump, but they are manually set at that speed. So I'm going to do the calculation. Yeah, that's great because the set point here is 5,000. So this point there is 3,000, 3,000, 5,000, and it's on pipe 90, 99. You can see that pipe 99. So everything is working perfectly. Now you go to your client or you're the operating company, you want to see what kind of failure can I have and what happens if there is a failure in the system. Suppose that pump stops working. You see, I can switch off that pump. can see that that pump has a dot, and that dot indicates that that pump is switched off. So I'm going to do calculation here. Oh dear, it's failed. Why? It is because this pump is stopped, and if that pump is still running at that speed, it is not enough to meet these set points here. If I reduce the requirements, maybe that'll be enough. But you know, this pump fails in an unpredictable way, unplanned trip of the pump, then you cannot change the set points very quickly. So what happens? The operator, he can see that something is wrong because if this pump trips, the pressure goes down and so on. So what does he do? He says, okay, I'm going to put this pump to run at its full speed. It's working. So if I increase the speed, it works. Except that here, see, the pressure is a little bit high. The first calculation that I did showed me that I need approximately 4 bar. This is almost 5 bar. What does it mean? It means that the control valves, for example, are less fully open. That's only 28% open and so on, because this pump is generating a pressure that's higher than the pressure we need. What is the consequence of that? Maybe the power consumption is a little bit higher than what it needs to be, because the pressure here is higher than the minimum required pressure, and which means that the control valves are not very much open. They have to create a big pressure drop. Now we can know that this pump is a variable speed pump, and I want to now find out, is it worth installing a control system? So the first thing is I look at the power consumptions. So it's 2078 kilowatts. It's quite a big power consumption. Of course, if I take that pump, that is 0 because that pump is not running. But how can I make this control system for the pump behave in an optimum way? It's because I know that the minimum pressure I need here is 4. So I can set, and that is node label 2. So go to the pump, and the pressure is 2. So the pressure is 4, and the node label is 2, which is that node here. So I will do the calculation. See all the required. Flow rates are met. I click on the pump. See, the pump requires of power as 1,644. See, that is approximately 25% reduction in the power consumption. So that gives you a way of deciding, should I use the variable speed pump or fixed speed pump, where the operator can change the full speed of the pump to its full speed, because he doesn't know what speed is optimum. So he switches that to its full speed. And so in this way, you can answer the question, is it worth installing a variable speed control system for this pump? One thing you can do from here is to move this to the transient module. At the moment, we're in the standard module. So what I can do, I've finished the demonstration with this system in steady state. I'm happy with the design. I want to now do dynamic calculations. I don't have to input the network again. I go to Tools, Utilities, Convert to Transient. I take the first case we looked at. See, PIPENET puts the file with an extension TM. So I can do the conversion now. That's the file I just created. I open that. See, this is a control valve, and that's a variable speed pump. Of course, there are controllers for these, and the standard module does not know the features of the controller. So you have to input, add the control system. And I've done that here. I've added the control system. See, that is the pressure sensor, and it picks up the pressure at that node. That is the transfer function. And what is the transfer function? You see, the physical pressure transmitter will have a little bit of time delay. The output signal from the pressure transmitter will not be the same as the pressure here. So this considers the dynamics of the pressure transmitter. So if you like, these two items together form the physical pressure transmitter. This is the PID controller. All the parameters for the PID controller are shown here. And that is another transfer function. Why is this here? If the PID controller tries to change the speed of the pump does not change immediately. There's a delay. The pump changes to the new speed over time. And that defines the dynamics of how the pump speed changes as a consequence of what the PID controller is telling you. So what is the scenario we're considering here? Here, as you know, there was a flow control valve, and that's a flow control loop. There's a flow sensor. That's the difference. Okay, and we can do some calculations. In this case, we're considering what happens if the pump loses power at 2 seconds and it spins down. I won't do the calculation now because we have so later on we will look at the dynamic part of PIPENET. So let's move on to now the sprinkler module, and that is for the design of fire protection systems. When Vietnamese engineering companies do work for overseas company, you will find that they would expect you to do fire protection systems using PIPENET transient module. So this is very, very important for you. So I will take an example. So I will take these are all real examples. This is a fire protection system. Fire protection systems in the oil and gas industry are very, very complex, and they're very difficult to design. And that is why PIPENET is the standard program for this. Every company is using PIPENET spray sprinkler module for designing fire protection systems. Now this here is a very typical on-show system. There are 2 diesel and 2 electric pumps. It's a very common arrangement. And with fire protection system, this is the fire water ring main. And when you're looking at the fire water ring main, that is what is called the worst case scenario. And because you cannot assume that the fire protection system is working completely. In other words, all the items in the network are working. For example, this here is a monitor, and that's off because you can see that because it has a dot here. Click on that. Then again, this is a hydrant and it is off. But these 3 systems here don't have the dot and they're working. So if I click on that, you can see that it is yes. So this is the worst case scenario. And so let's do the calculation. This is a real system. So we can look at the results. You can do that. Also, you can increase the font size. You can see that the nozzle deviation is 42.77%, 13.12%. So what do these numbers mean? So if I click on that, it selects that item, and you can see that we need a flow rate of 4172 liters per minute, but the actual calculated flow rate is 4719 liters per minute. So it's actually delivering about 13.1% more than what is required. Okay, so the system is working. So essentially, that's what this means. You get minus 100 because you need 946. Because it's switched off, it is 0. Now, you know, if you're an engineering company, you can take these results to the client. The client has to look at this and say, hey, this is good, but I want to see what's happening. He can even have a look at the velocities and all kinds of things. Of course, as before, we can look at the velocities, volumetric flow, and other things. But he wants to see how the pumps are working. Clicks on that. You can see it's working at that point, which is quite good. You can see the results here, 72 kilowatts. You know, the pump is, of course, running at full speed and so on. He's so happy. And then he says, what is the diesel pump doing? Diesel pump is running. It's the same power consumption. At this time, he gets a little bit worried, your customer, because typically a diesel pump and electric pump will not work together. So he wants to see what's happening with the other diesel pump. Oh, that's also working. So if you look at the flow rates, all 4 pumps are working. You see, in a fire protection system, not all 4 pumps must work. Typically, the design would be if there are 4 fire pumps, only 2 will work. So he says, listen, your design is fantastic, but you know, you're not supposed to have 4 pumps working. Can I see what happens if the 2 electric pumps are working, please? And you said to him, no, no problem. I'm using PIPENET. I can do things very quickly. See, pump on, switch it off, off. Right. See, the flow rate through these pumps have increased, but the other 2 pumps have gone to 0. So you can see that is from here, it's moved the operating point there, but it still is very good. Of course, the power consumption of the pumps which are working is increased, but these have decreased. So your client is happy, or your manager is happy. And the only thing is, hey, if we switch off 2 pumps, will the users still get what they're supposed to get? Yeah. See, it's fantastic. Look at it. You're getting 8%, 8.5%, 36.3% more than what is required. So your client is very happy, and your manager is very happy. He says, good boy. And then your client or the manager, they say, listen, we're going to operate this plant for 30 or 40 years minimum. And the fire is going to start where it wants to start. I cannot decide where it's going to start. So I may have to bring in some additional users. For example, I may have to start this hydrant, and also I may have to start this monitor. And you say to your client, hey, that's no problem. I'm using PIPENET. I can do this very quickly. Yes, as simple as that. And yes, so you can see the dot has disappeared. Do the calculation. Wow, look at this. These are still delivering more than the minimum required. These two are delivering a little bit less, but that is not a problem because these were not supposed to be working anyway, and if they're delivering 5% below what is required, that's not a huge problem. Okay, so this design is good. Everybody is smiling, and then the client asks you, oh, listen, there's one more thing I'm interested in, and that is because I have to operate this plant for a long time, it is possible that I have to block some pipes. For example, if the maintenance engineer closes some valves and then he forgets to open them, what will happen? Or alternatively, your client may want to see what happens if part of the system is not working for some reason. So it's very simple. I select the pipe. So the customer says, I've got valves on that line and that line closed. And you say to him, hey, that's no problem. Blocked. And blocked. You can see that it's put dotted lines to indicate the blocked pipes. Do the calculation. You know, this is a really beautifully designed system because even with these pipes blocked, it's almost working normally. You want 4172, we're actually getting 4140. It's only very, very slightly less than the required flow rate. And from an engineering point of view, For an engineer, this is acceptable when there is such a big failure in the system. So I wanted to show how quickly you can refine your design and you can build a story about how you achieved your design. Because, for example, if you're showing using PIPENET on your project, you can say to your client, do you want me to show you what happens if the pump fails? What happens if a pipe is blocked? What happens if you want to bring in additional users and so on? And that's all very, very good. Now, one thing I said I'll show you, I'll unblock these pipes. They're okay. What you may wish to do could be that you want to see what happens if one additional pump fails, in which case you can go to that pump and switch it off, do the calculation. You can, of course, if only one pump is working, then the system does not work. So let's go back to that and switch on the electric pump. Do the calculation. Go back to this, and the system is working fine. One thing that I mentioned earlier was the sorting facility. Now, this is not a very big system. This is a fairly small system, and you can see there are still quite a few pipes. If I want to see where's the pipe with the maximum velocity, click on the tab results. It shows all the pipes. I can search and search and search and find the pipe with the maximum velocity, note the label of the pipe, and then search here to see where is that pipe. With PIPENET, it is not necessary. You can do this in 1 second. Click, it reorders the pipes in increasing order and velocity. Some pipes have no flow, so the velocity is 0. And then I click again, it reorders the pipes in decreasing order of velocity. So I want to see where is that pipe. I click. That's one pipe. See how quick it is. I press the control button and click on the other pipe. That's also shown in red. So I want to decrease that velocity. I click on that. Increase that to, let's say, 200. Increase that to 200. See if I go to the results again. Click, click. See, all the velocities are now below 4.09. So I click on that, and that's a pipe with that high velocity. I want to keep all the velocities below 6. I've done that. See how quickly I did it. In the spray module, I would like to show you one other very important feature before we go on to the transient module. That is how to combine subnetworks and optimize them. See, in this network, we will consider this system here, which is that. Do the calculation. Whoa, look at this. It's too much deviation. If I click on that pipe and nozzle, you can see that we only need 85. We're actually getting 116.3, which is actually outside the recommended range for that pump. So what are we going to do? We should ideally be operating somewhere there. And that's because this deluge system is simply connected to the 5-water ring main. How will you design the system in an optimum way? So that is the question here. So in order to do that, first, I will take the deluge system on its own. And do the calculation. See, that's the deluge system on its own. And we use an option called the most remote nozzle option. Do the calculation. Look at the nozzle deviation. Change the font size. You can see that that is actually 0. So this is delivering exactly, you need 85, and it's delivering, and it's within the permitted range of the nozzle operation. And why did it do that? It's because I chose most remote nozzle option here. So what I'm, of course, interested in mostly is the pressure and the flow rate. I make a note of that because I need to achieve this pressure and flow rate at the inlet of the system. The problem in the previous case when I did the calculation was that I did not put any restriction. So what I'm going to do here now is scale. I'm going to move this. I'm going to open another copy of PIPENET. I'm going to open the network without that deluge system, because that deluge system was here. I've removed that. See, I noted that we need 4315.7. So I'm saying that the flow rate here is 4315.7, and I want to calculate what pressure the pumps will generate. Do the calculation. See, the pumps will generate 8.556. We only need 4.522. So we conclude that A, the system is going to work. We already know that because in the previous case, we had overflow through the nozzles. So what I want to do now is to put a restriction, because this is the pressure that's available and the pressure that is required is 4.522. So I need to put a restriction here. But to show what's going on, I will copy this, go to that. You must click on the area tool, edit, and paste. See? You can see that it's here. So I can right click, scale to fit. It's here. I can use the area tool to capture it, then take it to that position. See, so I can now connect it. Click on that. It's here. Now this is now an internal node. So click on that. It's not an output anymore. So I now do the calculation again. See, if you look at the nozzle deviation, of course, there are big values. Because I did not put any restriction. One option is to put a restriction orifice plate. And I know that I need a pressure loss of 4.033775. How do I know that? Because the previous calculation showed me the pressure available. I also know what pressure is required, and input that here, do the calculation. Wow, look at that. It's delivering exactly what is required. I can click on that. That'll show me the diameter of the orifice plate. If I want to see more decimal places, see, I can. So it gives me the diameter of the orifice plate. That's great. An alternative is to use what is called an elastomeric deluge valve, and I'll show you how to do that. Right click, explode that node, See, I'm showing you all this not just for demonstration. You should know that you can do all these things. It's a fantastic capability. See, I attach that valve there. That's elastomeric deluge valve. I select that valve. I can set the flow rate to 4315.7. Do the calculation. Go to the daily system. Nozzle deviation. So it is working optimally. So you can see how we can do a beautiful design. See, I'll show you one quite big network. It's not here. Go here. I think in Vietnam, you have offshore oil and gas industry. So this fire protection system may be interesting for you. This is actually from Qatar in the Middle East. They have an offshore platform complex. All these are offshore platforms. It's a gas field, and you can see how complex the network is. Listen, you can see that it's got more than 9,300 pipes, 13,000 nodes. I showed you how to copy subnetworks and combine them to build big networks. And that is the way this system was built. It is based on building complex networks from simple networks, because it's very, very difficult to build such a complex network pipe by pipe and nozzle by nozzle. It could be that there are different contractors or different engineering companies working on different platforms, or it could be that some platforms already existed and others are new, and so on. So this combining subnetworks to build big networks is a very, very useful feature in PIPENET. Let's go on to the transient module now. I will only show one example because we haven't got time. There are lots of different examples I can show you, but I will simply show one cooling for a system. The transient module is a very, very powerful program. And here, this is based on a system from a plant in China. It is called the Nanhai petrochemical plant. And you can see that the diameter of that pipe is 2 meters. Very big system. And there are 4 systems like this on the petrochemical plant. And so you can imagine how big the plant is. It's the biggest petrochemical plant in the world. And what they found was, first of all, let me show this. See, the cooling tower basin is at 0 meter elevation. All these elevations are negative. Why? Because these pipes are underground. It's quite common in petrochemical and refineries to have underground pipes. And what happened in this case was when they closed that valve here, there were severe vibrations. And because these were underground pipes, the ground itself was shaking. It was like an earthquake. And a friend of mine called Mr. Gosti from Italy, he actually was commissioning this plant, and he told me that he was scared because the ground was shaking. Why was that happening? See, this is a 2-meter pipe. This valve is closing in 40 seconds. It's not too bad. It's a reasonable closing time. But let's see what happens. This is based on a real system in China. If you, this valve 1, look at the inlet pressure. There's nothing terrible here. That's the way the valve closes. But what about the outlet pressure? Wow, look at this. The outlet pressure has got very severe oscillations. That's the reason why this system had such severe vibrations, and it looked as though there was an earthquake. So Mr. Gosti from Italy, he's a PIPENET user, and he wanted to know how quickly can we close this valve without creating big vibrations. See, the general rule is this is a fiberglass piping system. If you click on the pipe, you can see glass reinforced plastic. So it's a fiberglass. The rule generally with fiberglass pipes, the oscillation must be less than 1 bar. So the aim of Mr. Gosti was to close this valve in such a way that the oscillation or the amplitude of the oscillation was less than 1 bar. And I'm going to show you the scenario manager in PIPENET. Includes Perkins scenarios. Go to Tools, Utilities, Scenario Manager. But before I go here, I must actually save this, because I didn't save the system with that option where I changed that to include in scenarios. So now I go to Tools, Utilities, Scenario Manager, File. It's a new scenario I want to create. That is the file that I just created. You can put some description and so on. See, this is the specification. I can close the valve in 90 seconds. Don't forget the start time is 2. So these are the valve closure time. And then I create the scenario file. So generate. Now we can run. Okay, I can view the results. I can look at the maximum. Don't forget, there are 4 scenarios I created, and I can look at the tabular here. But what is more interesting is to compare the results in the graph viewer. You can see that these are the 4 scenarios, and you must keep a record of what the different scenarios are. The first one, if you're not sure, you can always look at the results. For example, you can look at the way the valve closes. But what we are interested in, basically, this is the original case where we had that very severe oscillations. I consider the next case. I can look to see this is a case where the valve closed in 90 seconds. Outlet pressure. You can see the oscillations are a little bit less. Last case. Okay, so you can see, and they have different scales. And you can see the scale by looking at the color. You can also have some really nice features, like, you can go and zoom in like this using the magnifying glass, or you can even zoom in through here. For example, you can change that to 20 and that 300. In that way, you can zoom in, and then you can move it like that way and that way if you like. Let's put this back to its original. Okay, so we got this 400 here. You can see that what we may want to do is the following. We can see this red line, the limit is 1 bar. That is way above that. But this one here, so what I can do is to select that one, which is this one here, and it'll give you the minimum and the maximum. But this is, see, 1.89 is here. So what I can do, because I want to keep the limit within 1 bar, see, I can show this line. So you can see that exceeds this 1 bar limit. So I can remove that as well. And this one here, you can see from the color that it corresponds to this. That's it. Oh, that's good, because this is below that 1 bar range for the oscillation that I wish to consider. But what Mr. Gossi did was to say, listen, this is a huge problem, so I want to be conservative, and this is not an emergency valve, so I would prefer to have a bigger margin in the pressure limits. So this is amplitude. It's only about half a bar. If you put half a bar limit, it's even then, it's within that. So he said, this is a conservative case, so I will choose this 240-second closure time for that valve. See how easily he was able to do the optimization of the system, and he used something called scenario manager. This is just an overview of the transient module. The transient module is a very, very powerful program, and there are many calculations you can do, such as very large cooling water system. I will not run this. I will just open it. See, this has got control loops, variable speed pumps with control loops, and flow control valves, and things like that. When I say it's a very large system, why am I saying that? See, if I choose that pipe, for example, you can see that that is 3.5 meters diameter. This was the very, very first system of such a big cooling water system that was built, and they used PIPENET for steady state and dynamic calculation. This design was done maybe 15 or 20 years ago, but the later systems, they had 4.5 meter diameter. Can you believe a pipe which is 4.5 meters in diameter? It really is very big. It's like a tunnel rather than a pipe. In fact, I visited this installation. It was quite amazing to see how big these pipes were. So I will finish now. There are a lot more things I can show you, but we don't have time. See, these are all process type of water injection, pipelines, loading system, LNG systems, all those things. You can also have fire protection process for offshore, onshore, FPSO, FLNG, and all those cases you can model using the transient module, the spray module. You can see there are many, many features here. And so even with the standard module, there are many things you can do. You can model ventilation systems, seawater systems, methane gathering systems, and so on. But anyway, we've come to the end of this session. I've taken slightly longer than we planned, and thank you for your patience, and thank you for being here. It's wonderful to see you all. We love to see our customers, so thank you for being here. So I hand it back to Ms. Tran and Victoria now, and I'll just say bye-bye. Thank you very much indeed. Bye-bye.
Thank you, Dr. Sebastian. I just wanted to mention that if somebody has any questions, you can send them in the chat, and we will spend no more than 5 minutes. And Dr. Sebastian, there have been 2 questions in the chat so far, but I suggest that we reply them by email because they are quite, I think, complex questions. You will not be able to answer them in a few words. So if you have any questions, please send them either in the chat or send them by email, and we will be very happy to answer your questions and provide you with more information. But if there are some like quick and simple questions, we can answer them now. So please, if you have any questions, write them in the chat right now. Okay, I do not see any further questions, so I suggest that we close this session. Thank you very much for your attendance. Thank you very much for your time. We understand it's already late for you, and we will be in touch. We will send you the video recording, and let me see. There's something else. Please advise how can we the reference density in this software. Advise how we can reference the density in the software. Sebastian, can you quickly show how we input density in the software?
Oh, see this fluid, and you can input the density, viscosity, and so on. This is a transient module, so you have to input things like the bulk modulus and so on. But if I open the standard module, the fluid, there are many options. You can choose water. You can see the temperature here. There are many options here. Direct specifications is probably the simplest one. You can use the density, viscosity, and the vapor pressure. It will use the vapor pressure to check if there will be cavitation. It has steam properties built in because, as you know, steam does not behave like a gas. It behaves differently, and the properties are built in. You can have gases. You can also have equations of state. So you can choose Peng-Robinson or SRK, and then define the composition of the fluid. So these are different ways in which you can input the physical properties.
Thank you, Sebastian. I do not see any further questions. So if you have any more questions, please send them now. Okay, I suggest we should not take any more time because it's quite late in Vietnam right now. So thank you very much for attending this session, and we look forward to seeing you again. Just like a quick word, if you liked the session today, very soon in August, we will have another training webinar in PIPENET, which is free, and you're most welcome to register and attend it, and we will cover many applications, further applications in PIPENET. So please visit our website, and you can find all the information and registration, and we will be happy to see you again at our sessions. Now, Ms. Tran, if you would like to say a few words of thanks and about further organization, please unmute yourself and say. And from Sunrise Systems in the UK, we thank everybody for the attendance, and we hope you like the session, and we look forward to meeting you again in the future at our events. Ms. Tran? Well, I cannot hear Ms. Tran. Okay, in that case, I suggest, sorry, there is something else in the chat. Oh, I see. Strange. Sorry, Ms. Tran, I don't know what happened to your microphone. I cannot unmute it. Oh, now it is unmuted.
Okay, it's okay now. Thank you very much, Dr. Sebastian and Victoria, for your support today with the webinar. Let me say a little bit in Vietnamese to say thanks to the participants right now. Thưa các anh chị, thì buổi hội thảo đến đây là kết thúc. Nếu như mà không có anh chị nào có câu hỏi thì là ban tổ chức CAC và công ty Solar System xin chân thành cảm ơn các anh chị đã dành thời gian tham gia hội thảo ngày hôm nay. Hy vọng hội thảo này đã mang lại những kiến thức hữu ích cho các anh chị và tương lai gần có thể ứng dụng các module của nền PIPENET vào công việc chuyên môn của cơ quan. Sau hội thảo này thì có ai có thêm câu hỏi hoặc là thắc mắc gì có thể liên hệ với em Trang CAC, hoặc nếu cần CAC và Solar System có một buổi demo hoặc là trao đổi sâu hơn về phần mềm thì là bên em rất là sẵn sàng có thể sắp xếp những cái buổi học riêng như vậy với quý công ty. Một lần nữa thì xin kính chúc các anh chị sức khỏe, hạnh phúc và thành công, và xin cảm ơn các anh chị đã tham gia buổi học ngày hôm nay. I finished, Victoria.
Thank you very much, Ms. Tran. Thank you. I will stop the recording now.